Okay, let me start my timer so I don't ramble for too long here. And yes. Oh, okay. Hi, my name is Thomas Gebert. That was a pretty good introduction. So I don't know if I can top that, but so this is the functional edge robotic testing with Boulder Studio and Clojure. So who am I? I'm a software engineer. I live in New York. I'm currently in New York. A PhD student part time at University of Old York. I'm a math enthusiast. I like playing with mathy stuff for reasons unknown. And I'm also a cartoon fanatic. And I guess I did use ChatGPT to come up with the title and the name for this. So I guess I'm a prompt engineer as well. So robots. Everyone here likes robots. Robots are objectively cool. If you don't like robots, then you should just leave. This is not the talk for you. Robots are cool. We should all agree with that. Is because they're hard to build. Because things that become easy to build, like refrigerators, they're cool in their own right, but they're also boring. But because they're hard to build, they're expensive, really expensive. So why are they expensive? Most things in tech require are just like software and stuff. But robots have actual physical matter you have to worry about, like with metal and resistors and diodes and transistors and all these things, all these isters that I don't know the names of. And so when you make a physical prototype, you have to plan it, you have to order and outsource parts from the outside world, and I don't like going outside. And you have to assemble them together with like a soldering iron. And that all takes time and money, and ordering from external factories can take weeks to actually get a result. So it's expensive. That has to come out into the cost of the robot. So that's no good. And also things break. Robots are exceptionally good at breaking. They're probably the best at breaking. So I kind of have an aphorism that I've been trying to get people to attribute to me, is that given it enough time, humans will convert everything into code. And the reason is pretty simple, is that computer and software are really cheap. Software is really easy to change if you need to change. We have undo and backspace and stuff. And I'm saying this at a software convention, so you all know this, but I'm kind of giving some pretext here. Software is easy to back up and version. We all Git or Mercurial or BitKeeper if we're feeling vintage. And software can, and this is a point that I don't think is brought up all that often, but I think it's important, is that software can be written by anyone. Like robots historically have cost a lot of money, and not everyone has a lot of money. So that's been relegated to really rich people or businesses. And so everyone else has to do, just sit there and feel bad about themselves. But software can make it so anyone can do that. You can buy a computer for nothing nowadays, and anyone can write code as long as they have hands and a computer and internet. So I put a pin in that. Think about that for a moment, and we'll circle back. So what is a digital twin? Digital twin. That's a fancy word. It's a buzzword in industry now, in mechanical engineering spaces. So what is it? So in the highest level terms, a digital twin is a digital representation of a physical product, and doesn't say much. So what does that mean over like a simulation? Well, it allows for a simulation of a cyber physical system before we build anything. So cyber physical system, it's the fancy way of saying embedded now. Someone told me that embedded fell out of fashion, so people just call it cyber physical systems now. But it's basically that. In doing this, you can avoid wasted time. And what separates this from a vanilla simulation and a digital twin is that it's a feedback loop. Simulations inform the real world design. That's obvious. But then the real world design can feed back in the simulation. An example of this would be like a wind tunnel. Wind tunnels have a physical simulation for like a wing, and they have a digital simulation in the form of a CFD program. And they feed into each other. The simulation is corrected by each one. Okay, so again, put another pin in this. This is all pretext. I promise this is going somewhere. So okay, so when we're designing things, robots or anything really that involves physical space, we need to model it somehow. And the most common way of doing that is CAD modeling, computer-aided drafting. And it lies somewhere between technical and art. I don't know anything about art. I don't like art. I'm an engineer in the purest form of the word, that I don't understand anything involving art. I'm just technical. But the annoying thing is that it seems like most of the CAD tools are not for me. And fun fact, if any of you want to start a business, apparently you can just start new CAD programs, because there are so many CAD programs. If I were to list them all, it would just, the entire 45 minutes would just be me listing out CAD. There's too many. We don't need that many. But I can guarantee you, just take a noun and add CAD at the end. That probably exists somewhere. So anyway, there's lots of them, and most of them are graphical, which kind of caters more to the artsy people. But it covers the entire spectrum of what you want. So for an example, like for like more like 3D models, like for engineering, you use like something like SolidWorks. For architecture, you might use something like AutoCAD or Revver. For FreeCAD, you might kind of use, it's kind of in the middle there. There's bunches of them though. But the annoyance of this is that GUI programs, you can't automate them. Not really. I guess if you want to do like vintage auto hotkey viruses, you could do that. But for the most part, you really can't automate GUI programs. Not very well. And because GUI programs kind of require humans to like mess with a mouse and stuff, they're really not reproducible. You kind of, if you lose the file or you lose the render, you kind of have to just do things again. And I don't like that. No one should like that. People seem to like that. And that's the worst. The worst sin is it can't use dim keystrokes inside AutoCAD. That's the unforgivable sin that I cannot think about past. So what do? Well, we're programmers, so we of course like plain text. You know, if you're going to Lambda days, you're obviously a very smart and enlightened human who understands that functional programming is much better than anything else. So we should use that somehow. So there is a way. There is a way, and I promise there's a point to this. There's something called constructive solid geometry. And that's kind of a fancy way of saying taking primitive shapes like cubes and spheres and cylinders, and then making complex shapes out of those things using Boolean operations like unions and intersections and differences, kind of like in a hand-wavy way, kind of like the set theory versions of those operators. And because this is all declarative in terms of unions, sections, and intersections, and differences, you can just kind of you can just do this in plain text as long as you have a declarative language. And I can't think of a paradigm that emphasizes declarative programming. Maybe you guys can tell me about one. I'm joking, of course. There's functional programming, and there is OpenSCAD, OpenSCAD. I don't know how to pronounce it. It doesn't matter. But it is an open source CAD program for all the major platforms. And actually, I did check. It really is on every major platform, because there's even a web-based version of this now you can play with. That I didn't make this. This is a donut that came pre-packaged with it. So you can use it on everything: Mac, Linux, Windows. I'm using the Mac version for my demos here, but it works on everything. It's a purely functional language. That's actually not quite true. It's mostly purely functional, which I acknowledge means it's not purely functional. But it's because you can import SVG files from the outside, so you can lose some determinism with that, but it's still mostly pure. It's a very declarative and compositional way of creating 3D models. I wouldn't probably make an art piece with it, but if you're making a design, it's very declarative and compositional. And everything's defined in pure plain text. It's not some fancy binary format that exists that you need some hex editor to mess with. It is just plain, UTF text. Excuse me. And objects are composed with primitive shapes, like using unions and differences and holes. And I did a dry run of this talk a few days ago with a friend, and he didn't know what a hole was. So a hole is when you have two objects and you kind of have a shrink wrap between them to stretch it out, so it fills in all the gaps in between. But and the point I want to emphasize here, why this is important, is that when you have access to a programming language, and that gives you everything a programming language gives you. This isn't some sort of facsimile, like pretending this is a real programming language with all the fun bells and whistles you think about programming. I mean, you get mathematical operations and variables and all that fun stuff, even recursion if you want to do that. So some basic syntax for OpenSCAD is you have cubes, a cube, which is actually more of a rectangular prism. If you have only one argument, a cube is just is a cube. If you want to do multiple arguments here, that's length, width, height for arguments there. You can do cylinders, which you can do named arguments here. So height is 10. You can do R or D for the radius and diameter, respectively. This center equals true it's kind of weird. I don't really know why. For some reason, when you do these things, they're not based, they do a corner on the origin instead of actually centering it like you'd expect. So just always do this. I always do, at least. And there's spheres, which are exactly as you think. Again, you can do radius or diameter. That can be useful depending on your measurement sometimes. So if you need to move things around, there's translations. Translations translate. It moves things. It's exactly as you think. It's X, Y, and Z. You can pass in an object into there. And rotations always rotate about the center, and you can choose which axis. So that's something you got to keep in mind. If you translate something first, then you rotate it. That can give you some unpredictable results. So that's something you have to just think about. But regardless, yeah. So you can rotate, and it kind of does what you think it does. So in this case, it'll rotate 90 degrees on the X-axis, 0 on the Y, and 90 on the Z. Or Z. I don't know what the best way to say that is there. I'll go back and forth. Differences are kind of what you think they are. You take the first object is the whole object, and then it cuts out whatever the following objects are. So this will carve a cylinder-shaped hole in this sphere here. Intersections in this case will be just the things that both things occupy. So like a set intersection. And the union just kind of glues them both together. You don't actually strictly need these in OpenSCAD, but they're kind of nice for just kind of a prettiness perspective. But anything in the global scope has an implicit union on there. But and the thing that was really sold me on this when I was first learning about this stuff, because I've been using FreeCAD for a while and hated it, was when I saw the loops. And it's like, because this is the thing that like brings it up to 11. Like otherwise, it's just kind of a text-based FreeCAD, but this gives you something that's not really easy to do in other languages, and that's just being able to repeat stuff. And I'll show an example as we go on, like how this is useful. In this case, this will just make a bunch of cylinders in a circle, but having loops is actually immensely powerful. This is actually closer to a map in functional because this all returns something. It's called for though, but it's closer to a map. With a range as an argument. And it goes from 1 to H here. This is the middle one's the step size. And you can also make modules. So if you end up doing a bunch of things, you can make one big old module, kind of like cylinder or cube or sphere. And you can just glue these together, and you might be seeing where this is going. So I union all these things together, and this makes a big capital H if you as an exercise for the reader if they want to play with it later. But then you can see I took that big H thing and it composes. You can just keep doing this, and this can go infinitely deep up to the level of whatever RAM your computer can hold. But this can go hundreds of levels deep. So and you can keep composing these things. So you can see I've nested. I've nested this big H, 3 times under a for loop, and then 3 more times under that. And this makes a big old like sphere of those capital H's. If you look at that, it's kind of weird. I was just trying to show an example, but let's look at it for real. Let's make a real thing that could actually be useful. So OpenSCAD, you can use any text editor you want, including Vim if you want. I'm going to use the built-in one, which is not good. I don't recommend it. But let's make something that's, I think, universally agreed upon to be useful. That's a gear. Let's make a gear. So a gear is basically a cylinder with some teeth sticking out in the end, right? In an even pattern. So one thing I have whenever I make physical models, the thing that I dread the most, and it gives me anxiety just talking about it, is measuring things. I hate measuring things. The worst part of my day is when I have to measure something. I don't like numbers. So it gives me anxiety. So one nice thing about OpenSCAD is since you have variables, you don't have to worry about that right away. So if I want to make a gear, let's say I want to make it like I don't know, 10 centimeters across. So so let's say gear diameter is, so everything's in millimeters. They say it's unitless, but if you export it, it's millimeters in your model in your 3D printing program. No, I'm kidding. Yeah. That's as big as it goes? Is that better? Okay. Uh, so maybe is that better? That's as good as big as it goes. I was unprepared. I have a solution, but it's not a good one. Uh, 1 second. We see I have technology, and that technology is Vim. So 1 sec. I can do this, and then um, 1 sec. I'll make this bigger. Don't worry. I came prepared. NVim test gear dot scad. Okay, and let's make this. I'll make this as big as I want it to be, and I'll just shrink wrap this guy. Okay, so if I do now, how does this look? That better? Again, I am using Comic Sans, but okay. So okay, so say we want to have actually as big as I can get it. So if we're making a gear, we want to have a diameter of it. It's because a gear is basically just a cylinder with teeth. So let's make the diameter diameter equals 100 millimeters. And then a gear thickness equals, let's make that about a centimeter tall. As I say, num teeth equals, let's say we want to just do like 10 teeth right now. Tooth width would be something like I don't know, say 5 millimeters. And just to give you something pretty to look at while I'm doing this, we can do cube, or let's use cylinder of h equals gear thickness and d equals gear diameter, and then center equals true. Yeah. Oh, you're gonna do this to me? Why? Okay, well, yes. There we go. Okay, all's good. So we got a cylinder. There's a watch. OpenSCAD does a watch on the file. So if you just reload the file, if you save the file, it'll reload. So you can see immediately after doing this, it created the cylinder. That's not a gear. It doesn't even look like a gear. It looks like a cylinder. It's like a coin. So let's actually fix that. Well, I think we all agree gears are universally useful. So actually, let's make a module for this real quick. Gear, and we'll say thickness, diameter, or should say D. Num teeth, and I can make this a bit wider because I have looking out of room if we don't. Num teeth, tooth width. We can add more later. I think that's all we need for right now. And if I do this, it's going to go away. And you're going to say, why did it go away? It's because I just defined it. I didn't actually instantiate it. So let's fix that. So that'd be gear thickness, gear diameter, num teeth, tooth width, and it's back. So because we just, all we did module does is define it. So this is not a gear. So let's so a gear needs a tooth. I think that's not a controversial statement. So a tooth can just be a cube that juts out. So for now, let's just comment him out and make our cube first. So cube, and we'll say it is, I believe we can do tooth width, and then we're going to say tooth length. Say, I don't know, let's say a centimeter. Tooth length, and we want this thing to be the same height as the gear, so that'll be thickness. There. That was my nickname in high school. So okay, so we have our thing there, and I just realized I think I got a parameter backwards. One sec. Oh, we also want to center it too. Center equals true. And if I wait, that seems wrong. One sec. Technical difficulties here. I'm sorry. Oh, I see. Yeah, gear diameter. You are right. This is what you get for staying up to 5 in the morning there. But that didn't actually fix the problem. But I have this already written down here if I need to. But let's see. No, I see. It's what? Oh, I forgot I don't have the final thing. Tooth length. That'll do it. There we go. Okay, there. Slight mishap. I'm gonna blame it on being tired. Okay, so you might notice this is being enveloped by the cylinder here. So we need to shift it. So let's do that. So translate. Let's just translate it. The diameter divided by 2, d div 2, and 0, 0. Right? And we don't actually need curly braces for this yet, but I'm going to do it anyway because, Okay, and we actually, well, this will be good enough, but it's kind of wrong. Plus 2 or tooth length div 2. Oh no, I was wrong. I was right the first time. I should make the tooth length longer. Oh, because I got the width and length backwards. There we go. That's what I wanted. Okay, so that's still not a gear. It doesn't even look like a gear. It looks like a broken ping pong paddle. So we need to get more teeth here. So let's do that. So we can do for I equals, let's say we can do 1 num teeth, that, blah. And after we translate it, we need to rotate it. Rotate of across the z-axis. So 0, 0, I times 360 div, that's 360 div num teeth. And we do that. We also still don't need curly braces here, but I'm going to do it anyway. Don't put a 0 there. That's wrong. There we go. We have our teeth. That's not really a gear, but we can kind of play with the values here. So let's put say 50 teeth over here. That's too many. Let's do 20. Okay, so that's pretty cool. And you might have seen, and also there's really no way to mount this. Let's do something else here. So let's make a first union all of these just for posterity. And okay, so we have that. So that doesn't change anything. And then we need to punch a hole in the middle so we can actually mount this or glue a rod through it. So let's do a difference. And difference. And then we just need to do another cylinder. And I can give a variable here, but just for fun, let's just do h equals, and I can put whatever I want here because it just has to be thicker than this. Center equals true, and d equals, I don't know, 10. And there's a typo somewhere. Oh, you need semicolons. Always need semicolons. There. So we have that. And of course, I can make variables for these two if I wanted to as well. I could do whatever I wanted there. And then, so now I have a module and I have a gear. And of course, if I wanted, I can make another gear. Oops. Here, translate, 0, 0, 100. Oops. Of, so the same thing. And this is cool, I think. And what I like about this, and so say you built this model, and then you're happy with it, and then your boss comes along saying, no, the client only wanted 18 teeth. And so instead of having to go and redesign, respace and reapportion this stuff out, you don't do that. You just change one number, and everything will just magically fit on there. And these are parameterized, so I can change whatever I want here. So if I want the second one to be smaller, I can do, oops. I don't know, I can do, 14. Oops. I can play with these numbers here and just do all these fun things. And so, yeah, OpenSCAD's cool. You should use it. It's fun. Back to our regular scheduled broadcast here. Let's go back. Okay. So I mentioned this a few times already, but I'll mention it again. So the reason you use OpenSCAD typically is for 3D printing models. So if you're going to a technical conference, you're familiar with what 3D printing is, obviously, but it also lies somewhere in the middle between technical and art. You can throw in frustration maybe as a third point there, but the nice thing about 3D printing is it kind of gives any human who can has $200 the ability to have manufacturing at home, and that's quite powerful. It's and of course, even for a corporation who has much more than $200, it still decreases turnaround time. You don't have to ship things off the factories or anything like that. You can quickly get something iterated in a few hours instead of a few weeks. But of course, there are problems with 3D printing. Because printers break a lot. You're gonna, if you buy a 3D printer, even some of the newer good ones like by Bamboo or something, you still have like hot ends that end up breaking, or the gears will break, motors will break, everything, and you'll fix them, and then they break again. That's just going to happen immediately after you fix them. You get like one print, and then it breaks again, and then what will happen is you have a print that is about 2/3 of the way done, and then something will break off the plate, and then it screws it up, and you have to start over. You just wasted like $40 of filament. And even though printers are faster than shipping off to China, it's still slow. It's still not ideal, really. It's still way slower than you'd like. And resin printers have a whole separate carcinogenic issue of the fumes are toxic, and you don't want to deal with them that often, and then you have to get them and dip them to an alcohol bath, and then the alcohol itself can't be used for anything because now that's toxic. And if you're an idiot like me, you spill the resin all over the floor, so you have to get in a hazmat suit and UV cure your entire floor. And that actually happened. Not recommended. And sometimes what will happen is you'll spend a whole week working with broken prints. It'll finally finish after like a week of getting things, and you find out, oh, it's off by a millimeter. Damn. And you have to do the whole thing again. And sometimes a drill can save you in that case, but usually not. Usually you have to do it all again. So that's no fun. So we want to minimize the number of 3D prints. We want to minimize how many prints you actually have to do. The fewer, the better, really, because they're expensive too. So there's a whole slew of things to kind of test 3D models beforehand. And one of them is called Capelliasim. This is an industrial product. It's Wikipedia sort of lies here. It's not really open source. It's open source-ish. It's mostly proprietary, but it is free for personal use. So it's premium. And if you're using a professional thing, you can upgrade it. You can import 3D models and run simulations on them. And you can program it via Lua, for better or worse. And so let's look at a quick example of this. And I already have it open, at least it should be. So this is one of the default models you get with to play with. I modified it a little bit, adding a helicopter in there because I thought it'd be fun. But this is just a 3D little model of a sphere, and there's a little basic Lua code that I wrote there. And if you do this, you can see it has a little sensor to look here, and it can turn when it kind of gets into the proximity of the helicopter because the box is giant there. And ideally, it doesn't always work. This is a little less deterministic than I like. If it hits the edge, it's supposed to detect the edge and turn. Let's see if it does. It's kind of funny to watch it fall off. So I didn't always do that. It's not perfect, and the people who know what they're doing more can make it work better. But it's still pretty cool, and people do use this in industrial stuff. So it's not any problems with it are on me, not in the simulation really. And you can, of course, there's pre-made stuff like arms you can play with, and it's kind of fun just to watch the chaos that can ensue. It's just kind of randomly going. But you can do real stuff with this. This is kind of a go-to for intro to robotics classes if you take one in an undergrad class. But you can do some cool stuff with it. So if you guys are interested in making robots, this is free for personal use. If you're going to sell something, you have to pay them. I think it's $300 a year, 300 euros a year. So, but if for personal use, it's free. So you play with it if you plan to do something with robotics. But that's just a quick one. So back to the thing here. Oops. So the disadvantages of Capelliasim is that Lua is not a functional language. I don't know what the hell Lua is. Someone explained a meta table to me once, and I don't remember anything about it. I wasn't really paying attention. And Lua is weird. It's not a functional language, so of course it's not good. And there are kind of sort of ways to kind of go from the model to the 3D printer, but it's really not meant for that. It's sort of meant for you kind of have to fidget around, like exporting from SCAD or something into an STL or into an obj file, and then import that, and then link that into your application there. And you can do that, but it's just annoying. It doesn't really let you edit the model directly within the program either. There's some tweaks you can do, but it's pretty minimal. You really need to do it in a proper CAD program. So this is all sort of introduction. So Boulder Studio is an open source CAD and digital twin simulation toolkit. It kind of combines the best of Capelliasim and OpenSCAD into one nice playground. It's great and it's free. You should use it. You can use pretty much any JVM language, Java and Kotlin and Groovy and Python and Clojure. Don't use Python for this unless you just have way too much free time, because the Python just takes forever to load anything. It's super slow. I don't know what kind of weird things Jython isn't doing, but it's horrible. But every other language here is fine. Even though I hate Java because I'm enlightened. It's actually, the Java implementation here is not so bad. It's actually fairly okay. My Clojure, of course, is the best. And it can simulate. It does a lot more than I can cover in this talk. So if it seems interesting, just Google it or Coggy it. But it can do a lot. It can simulate lots of stuff. It can simulate motors and physics and collisions, and you can even hook in like an Arduino and actually have it like run simulations directly on the Arduino, like powering everything. It's really cool. I'm kind of geeking out as I'm talking about it, but so it has a built-in thing called JavaCAD. And it's very similar to OpenSCAD. I'm pretty sure it was inspired by it. And it uses pretty basic Java methods to build more complex shapes. So we don't want to use Java. We want to use Clojure. So we can make sort of a wrapper DSL real quick. So if we do that, so you can see we're getting the same objects as you get with OpenSCAD. And it's actually not, you can see this is the Java API. It's not too bad. But so we're just kind of wrapping around stuff. The reason I'm doing the double X here is because otherwise it will not automatically convert your integer. If you type an integer there, it won't automatically convert it. So just put, I always, there's no, in this stuff, you always use floating points anyway. And these are, this is the number of surfaces you have. 200 seems to be the best performance to quality ratio. And these are just the move functions: move X, move Y, move Z. And these are just wrapper things for the translate. And if you wanted the OpenSCAD version, you get the move and then do the same thing. If you, those who are paying attention might have noticed this guy. This is the function application, like the pipe in F#. It applies things to functions. And you might have noticed these are just functions. These aren't some wacky Clojure construct or some wacky like Java CAD construct. These are just vanilla, boring Clojure functions, meaning we can use Clojure composition operators on there without having to worry much about it. And then we wrap the rotations as well, rod X, rod Y, rod Z. And then to get the OpenSCAD thing, we do the same thing. And then it's just composing all three of them, whatever they're in. So we do the same thing. And we have similar operators. Again, because these are just vanilla Clojure functions, we can use vanilla Clojure compositions. And so this is not a fancy, a Bowler Studio reduce. This is just the Clojure reduce function, calling across all the objects you pass in there, and it just unions them or does the difference between all of them or the intersection. And I wish I could say I took credit. I copied this from the Java CAD documentation. This is not my clever thing. I wish I could take credit, but I did modify a couple of these things, but this is still kind of mostly someone else's work. So, and like OpenSCAD, there are loops. You can also use for loops here in Clojure's for loops. I, for some reason, always use maps, but it's kind of the same thing. I had trouble getting the regular vanilla map working. I had to use map V. I'm not 100% sure why. It seems to have problems with the lazy sequences. Whatever the reason, let's just keep that in mind. But so the capital H thing I did in OpenSCAD a few slides ago, that's the same. This is the same thing here in Clojure. And so we can play with it in action. And so I will say, if anyone here knows the people who work on Bowler Studio and or knows anything about developing stuff for Eclipse, please fix the interface on Bowler Studio, because it's the only thing I don't like about it is the interface is not good. And it also eats memory like nothing else. So that's a little annoying. It's worth it. It's cool, but you kind of have to just take the bad with the good here. And it takes a second to load up here too. If it wants to load, it'd be great if it loaded. There we go. And also, I really dislike that it requires you to link it with GitHub, but that's okay. So I ported over that gear we did earlier. I copied over those operations I did, and I ported over the gear. And we don't need to go through it again in too much intimate detail. It's a cylinder, and here's the teeth with the map here, range, num teeth, and it's just a vanilla Clojure function that calls it. And I'll get to the rest of this in a second. I'm kind of spoiling it here. That's no fun. But if we run this, you can see this, and look at that. We got the same gear, right? Isn't that fun? And you're probably thinking, well, that's not really that great, Tom. That's the same thing you just showed us. And I agree. That's not that great. I don't want to waste your time. So, but one thing that you get with Bowler Studio that you don't get with OpenSCAD is the ability to do this. So you got to clear this first. If you run this, give it a second here. It's going to work. It better work. Look at that. We got physics. We got physics, baby. Look at that. There's collisions. There's physics. I'm going to do it again. It's so much fun. Look at that. So it'll clear. Yeah. So we got physics, and this is immensely powerful, more powerful than just dropping gears in funny shapes. There's a lot of stuff here. If I wanted to go into all the details, here. It'd sadly be a crash course and everything. So I'm going to steal someone else's code real quick. And one thing that's nice about this is it comes with a bunch of pre-made models you can play with. The one I'm going to show here is called the Grasshopper. And you can do a lot of stuff, and it's constructing it on the fly. Is this doing the same kind of Java CAD I was doing here? Though it's using Groovy in this one then instead of Clojure because they haven't seen the light. And if we want to look at the CAD model here, it's this kind of cool thing. If it ever constructs. I swear this was faster earlier, but of course, as I'm presenting, it's going to slow down because I think I'm running a little low on time. Okay, I'll be quick. Don't worry, we're almost done. Okay, it's done. So one thing you can do, you can start simulating the movements of these things. So in this particular case, we can turn on the physics simulator. We turn that on and go back so that we have this, we have running, and now we can make it walk. And so we can do that. So we can make this walk, and we can make this rotate. And the thing is that this is running the same code that would actually be running the real robots. This is actually running the real same Arduino code and everything. And you can right click, export to STL. And STL, for those who don't know, is the typical 3D printing format. So I go in here and I can actually export it to an STL file and then print it. So I have an end-to-end means of modeling, testing, and printing the robot. And I think that's super cool. And you can also actually plug in a game controller to control it. I'm not sure how useful that actually is, but I think that's really neat. So we're almost done. Let's go back to the slides here. So in conclusion, you should go build some robots or at least do some programmatic CAD stuff. It's really fun. It's really cool. It's relaxing. People will think you're cool for doing it. The important part I want to get at though is by using the code-based stuff, you can automate the computer do more work for you because it's no fun to do work on your own. Let the computer do as much as possible. And when you build a robot that takes over the world, remember the cool guy that taught you about all this stuff. And when you're enslaving humanity, give me a slightly better prison cell. And so, yeah, I don't really do social media. But you feel free to email me if you want to talk about any of this stuff. And that's pretty much it.